Myself, Dr. Susmitha. I am working as Assistant Professor in Chemistry in Institute of Aeronautical Engineering. Today, we are going to discuss about estimation of hardness of water by EDTA method. By end of this topic, you will be able to experimentally determine the hardness of given hard water sample by complexometric method. The complexometric method is also called as EDTA method. Yes. Before entering into the experimental procedure, let us discuss about the type of volumetric titrations. There are mainly 4 types of volumetric titrations. One is the acid-base titration, redox titrations, precipitation titrations, and complexometric titrations. Talking about the acid-base titrations, the name itself indicates acid and base, means the acid and base reaction will take place in these type of titrations. Talking about the redox titrations, means the reduction and oxidation reactions will take place. The chemical volumetric titrations where oxidation and reduction reactions will take place come under this redox titrations. The next one is precipitation titrations. In these type of titrations, there will be formation of some precipitates. That's why it is categorized and named as precipitation titrations. Talking about the complexometric titrations, there will be formation of complexes. Means the metal and ligand complex formations will take place during the volumetric titration. That's why it is named as complexometric titrations. The name itself indicates what type of reactions will take place in the titrations. Now, today our experiment, that is the estimation of hardness of water by EDTA method, come under complexometric titrations, that is this one, last one, that is complexometric titration. This complexometric titration, if you see, as already I told, there will be formation of some complexes, means metal and ligand complex formations will take place. Here, the calcium and magnesium will form complexes with the reagents that are used in this titration. Now let's get into our experiment, that is estimation of hardness. The chemicals that are the important chemicals that are used in this titration are EDTA, that is ethylene diamine tetraacetic acid. The next one is a EBT indicator, that is aerochrome black tea indicator, and buffer solution. Added to this, the hard water sample and the standard hard water solution are also there. But the important reagents that play important role for this titration to take place are EDTA, that is ethylene diamine tetraacetic acid, and aerochrome black tea indicator, that is the name of an indicator, and ammonical buffer solution. These are the 3 important chemicals or reagents used in this titration. Now let us talk about these reagents in detail. First one is EDTA, the name itself. This is C, ethylene, E, diamine, D, tetra, T, acetic acid, A. Very easy to remember. EDTA, that is ethylene diamine tetraacetic acid. If we talk about the structure, already it's there, ethylene. See, if one carbon is present, the prefix we use is methane, methene, methine, like that we will be using. If 2 carbons are present, we will be using the prefix eth, means ethane, ethene, ethine, like that. If 3 carbons are present, we use the word prop, means propane, propene, like that we will be using. Here, our chemical, our reagent name is ethylene, means 2 carbon atoms will be present. So, if you see the structure, this is 1 carbon atom and this is the second carbon atom. So, 2 carbon atoms are present, that's why it is named as ethylene. Di means 2. Okay, diamine means here added to these 2 carbon atoms, amine means an ammonia, NH3 is called ammonia, amine means NH2. Okay, Diamine means 2 NH2 groups are there. That's why it got the name diamine. Di means 2, amine means anyways nitrogen will be present. That one you have to keep in mind. Then tetraacetic acid. Tetra means 4. Acetic acid, you know the molecular formula of acetic acid, CH3COOH. It is acetic acid. These acetic acids are 4 in number. That's why it got the name tetraacetic acid. So this ammonia, this hydrogen, 2 hydrogen atoms are there, no? These 2 hydrogen atoms are replaced by the acetate group, that is CH2COOH groups. Okay, the name, if you remember the name, the drawing of the structure or remembering the structure is really very easy. As I told earlier, ethylene means 2 carbon atoms, diamine, tetraacetic acid. Tetraacetic acid. This is all about the EDTA structure. Generally, EDTA as such, it is not used in acidic form, but the sodium salt of EDTA is used. Means this hydrogen will be replaced by the sodium salts. Sodium salt of EDTA is generally used during the experiment. Okay. Now, talking about the complex formation, the EDTA, it will form very stable complexes with metals. EDTA, it will form very stable complexes with metals. This point is very important to remember during the performance of this experiment. EDTA, it's done. EDTA, ethylene diamine tetraacetic acid, and EDTA, it will form very strong complexes with metals. Now, our second reagent is aerochrome black tea indicator. In short form, we call it EBT. Most of the times, the students will get confused between EDTA and EBT because both of them will start with E. They will be confused. But EDTA, it is the reagent that is used in this titration, and EBT, it is the indicator that is used in this titration. This aerochrome black tea indicator is just a normal indicator, just like how phenolphthalein, methyl orange, just like what will be the role of phenolphthalein and methyl orange? These are the general common indicators that are used in acid-base titrations. They will indicate the endpoint. Similarly, the aerochrome black tea is also an indicator which is used in volumetric titrations, and it will help us to indicate the endpoint of the titration. If by giving a color change, initially one color will be there, or initially it can be colorless depending on the type of indicator. The indicator by end of the titration, there will be a color change. That's why it is called the indicator. The name itself tells us indicator, means it will indicate the endpoint of the titration. So, in this experiment, we are using the EBT indicator, that is aerochrome black tea indicator. So, if you see the structure, this is the structure of EBT indicator, and here hydroxyl groups are present, right? This EBT indicator, when it comes in contact with the metals, it will form complexes. Okay, those complexes that are formed by the EBT indicator are unstable because in our water, what are the ions that are present? Calcium and magnesium. If you see the first part of the video, I told hard water means calcium and magnesium ions. So, when the calcium and magnesium ions comes in contact with this EBT indicator, complex formation will take place. At these places, the calcium will come and form a total complex will be formed, and this will give the wine red color to the solution. When calcium and EBT complex is formed, wine red color will be obtained to the solution, and this calcium EBT complexes are unstable complexes. Just know what I told, calcium and EDTA complexes are stable complexes, but calcium and EBT complexes are unstable complexes. Fourth one, the third solution is buffer solution. What is the role of a buffer? Buffer means they are the solutions which will resist the change in pH. If I add buffer, that will resist the change in pH. This can be better explained by taking a very good example. Okay, I have taken water in a glass. Now, you know the pH of the water, generally it is 6 to 7.5. Let us take it neutral. The pH of this water when I tested is 7. Now, I will add lemon to it. When I add lemon, the pH of the water will change. It will become acidic because of the acidic nature of the citrus acid. Lemon means it is acidic in nature. Lemon juice, it will be acidic in nature. So when I add this lemon to the water, the pH of the water will change. But I doesn't want the pH to convert into acidic. I want the pH at 7 itself, or I want to maintain the pH as such. So even after adding lemon also, if I want to maintain the pH of this particular solution as in the initial stage, I need to add buffer. If I add buffer solution, then pH will not change. If I add buffer solution to this water, even after adding lemon also, pH will not change. That is called buffer solution. Buffer solution means it is not allowing the pH to change even after adding some other reagents. Okay, these buffer solutions are of two types, namely acidic buffers and basic buffers. Acidic buffers and basic buffers. Acidic buffer solution and basic buffer solutions. Talking about the acidic buffer solutions, these solutions are generally used to maintain the pH in acidic medium. For example, I am conducting an experiment at pH 2 to 3 and I will be keeping on adding the reagents. During titration, we need to add reagents. So if I keep on adding the reagent, the pH may convert itself into basic medium. So in order to stop this, in order to maintain the solution in acidic medium, I need to add acidic buffers. If I want to maintain the solution in basic medium, I will be adding basic buffers. Okay, this is the use of buffers and the types of buffers. So we are talking about these buffers because in this experiment we will be using ammonical buffer solution. Ammonical buffer solution means it's a basic buffer. Means, see, this ammonical buffer solution will maintain basic medium. That is clear. And this experiment, that is estimation of hardness of water by EDTA, must be performed only in the pH medium of 9 to 10. If at pH 9 to 10 only, the complex formations will take place. That's why we will be adding buffer solution, that is ammonical buffer solution. Here ammonical buffer solution, it is prepared by the combination of ammonium chloride and ammonium hydroxide. Okay, ammonical buffer solution, it is prepared by the combination of ammonium chloride and ammonium hydroxide. Okay, this regarding the complex formation we will discuss in further slides. As if now we are using three important chemicals, that is EDTA, ethylene diamine tetraacetate or tetraacetic acid. It is a reagent. Second one is a EBT, that is EBT indicator, and third one is buffer solution. EDTA, it will form strong complexes with calcium and magnesium ions. EBT, it will form unstable complexes with calcium and magnesium ions. Now, let me give a brief introduction of what will happen in this experiment. Then we will jump into the principle and procedure. See, already I told what is hardness of water. Hardness of water is caused because of the presence of chlorides, sulfates, nitrates, carbonates and bicarbonates of calcium and magnesium. That's one you know. Okay, hard water means what should come into your mind? Hard water means calcium ions or magnesium ions. Both are responsible for hard water, hardness of water. So and one more thing is total hardness. Total hardness means permanent hardness plus temporary hardness. What's the difference? Temporary hardness and it can be removed easily. Permanent hardness cannot be removed easily. These are the 2 points which you have to keep in mind while doing this experiment. So in this experiment, what you people will be doing is, our aim is to estimate the hardness. Our aim is to estimate the hardness of water by EDTA. EDTA, it is the reagent used in this experiment. Okay, that's why it got the name EDTA method, because we will be using EDTA in the reagent as a reagent in this experiment. So first, in the conical flask, what we will be taking hard water in the sense calcium and magnesium, hard water, and we will be adding the indicator. Why do we add indicator? To indicate the endpoint of the titration, and buffer solution. Okay, in conical flask, we will be taking hard water, indicator and buffer solution. And in the burette, we will be taking EDTA. Okay. In conical flask, we will take hard water, EBT and buffer. Now, what will happen in this conical flask? It will be wine red in color. Once you start adding EDTA to this solution, this wine red color will turn into blue color. Wine red color will convert into blue color, indicating that experiment is done and you have to stop adding EDTA to this solution. So, the general experimental procedure is take hard water, EDTA, EBT and buffer solution in the conical flask, and then add EDTA in the take EDTA in the burette and then add it to the conic contents in the conical flask till blue color is obtained. This is a general experimental procedure. So when we when blue color is obtained, the volume of EDTA that is consumed is considered. The volume of EDTA consumed will be proportional to the amount of calcium and magnesium ions that are present in water. If calcium and magnesium ions are present more quantities in water, then more volume of EDTA will be consumed. That is the main general principle that is followed here. Let us get into the principle. What did I told earlier? In the conical flask, we will be taking hard water, indicator and buffer. Hard water, that is EBT indicator and buffer in the conical flask. So, when hard water comes in contact with EBT indicator, already I told EBT, it will form weak complexes. So, the metal in the sense calcium, okay, calcium or magnesium ions. This metal will form weak complexes with the EBT indicator and it will be wine red in color. So, the first thing that will happen is when you take a buffer solution, indicator and hard water in conical flask, wine red color is obtained. Why this wine red color is obtained means the metal, that is calcium or magnesium ions, will go and combine with the EBT indicator and form calcium EBT or magnesium EBT complexes, which are wine red in color. These are unstable complexes. Once we take contents in the conical flask, what we will do? We will keep on adding the EDTA to the contents in the conical flask. When we start adding EDTA to the contents in the conical flask, the color change will happen. Slowly, the wine red color disappears and blue color solution will be obtained. When we obtain the blue color solution, we have to stop the titration. That is clear. Now, during the formation, why this blue color solution is obtained means, when you start adding EDTA to the solution, this EDTA will replace the EBT. Means metal and EBT complexes are unstable. When metal sees this EDTA, so as I am unstable, this metal wants to attain stability. Means the metal will think I am very unstable. If I combine with the EDTA, I will become very stable. So in order to attain stability, the metal, it will leave behind the EBT and it will combine with EDTA to form metal EDTA complexes, and EBT will be left over. Once all the metals, that is once all the calcium and magnesium ions that are present in water combine with EDTA, then the blue color solution is obtained. That blue color solution is because of the EBT indicator. Here wine red color solution is obtained because of metal EBT complex formation. But here blue color solution is obtained not because of complex formation but because of EBT indicator. Now if you see the example here, it's already written. Instead of metal, I have just written the calcium, because hard water is nothing but calcium and magnesium ions. Here see, calcium, it is present in hard water. We are taking hard water. EBT, it is an indicator. Anyways, buffer solution, in order to maintain pH 9 to 10, buffer solution anyways we will add. This calcium, when comes in contact with EBT, it will form calcium EBT complexes which are unstable. Okay. Now, when we start adding EDTA, these calcium EBT complexes which are unstable, they will dissociate and this calcium will come and combine with EDTA to form calcium EDTA complexes, and these are stable complexes. Okay. This is the main principle. The principle is very simple. Hard water means calcium and magnesium. In conical flask, we will take hard water indicator buffer. So, when hard water means calcium and magnesium, already know, calcium and magnesium, it will combine with EBT to form complex. Metal EBT complex or calcium EBT complex. When we start adding EDTA to this, what will happen? The metal EBT complex, it will dissociate and again the metal will combine with EDTA to form metal EDTA complexes. Why the metal is leaving behind EBT? Why is it combining with EDTA? Means the metal, it will form stable complexes with EDTA than EBT. That's why it will leave behind EBT and it will combine with EDTA. Okay, once endpoint is obtained, blue color solution, blue color will appear in the conical flask and we will stop the titration. This is the main principle that is employed in the titration of EDTA, estimation of hardness of water by EDTA method. Now, talking about, before entering into the experimental procedure, let me introduce you two important terms, that is standard solution and the sample solution. In general, the standard solution term is used for the solutions whose concentration is known. Means there is no need to calculate or don't need to find out the concentration of that particular solution. So, the solutions of known concentration. Solutions whose concentration is known are called standard solutions. But sample solutions, the term sample solutions is generally used for the solutions whose concentration we have to find out. So, in our experiment, the sample solution is hard water sample, whose hardness we have to calculate. Okay, that one we call it hard water sample. Now, standard solution means in this experiment, there are mainly 4 steps. First step is preparation of standard hard water solution. First step is preparation of standard hard water solution. Second step is a standardization of EDTA. Second step is standardization of EDTA means EDTA concentration we don't know. In this second step, we will find out the concentration of that EDTA. The third step is estimation of total hardness of water. Means estimation of total hardness means permanent hardness and temporary hardness. Both hardness combinedly we will find out in the third step. Fourth step is estimation of permanent hardness of water. So, in this step, we will calculate only the permanent hardness of water. Fifth one will be the a calculation of temporary hardness, which is a simple subtraction. Subtraction procedure will be there. So, in the estimation of hardness by EDTA method, there are mainly 4 steps, that is preparation of standard hard water sample or hard water solution. Second step is the standardization of EDTA. Third step is estimation of hardness of water. Now let us see how these steps are performed. The first step is preparation of standard hard water solution. Means here we can choose calcium carbonate or magnesium carbonate, anything we can choose. But I have taken this calcium carbonate. For this step, we need to take some 0.5 grams of calcium carbonate and dissolve it in HCl. We need to take 0.5 grams of calcium carbonate in 100 ml conical flask. Means we are preparing 100 ml of standard hard water solution. So 0.5 grams of calcium carbonate is taken and it is transferred into 100 ml volumetric flask. Volumetric flask, they will be like this with a long neck and lid will be there. Okay. These are volumetric flasks. Conical flask means these are conical flasks. Okay, volumetric flask will have a very long neck and conical flask, they doesn't have that long neck. Okay, now 100 ml volumetric flask is taken and to this 0.5 grams of calcium carbonate is added. Now, as already I told in my previous video, the calcium carbonate, it is insoluble in water. That is the reason why we have chosen calcium carbonate to express hardness of water. Hardness of water is always expressed in terms of calcium carbonate equivalence. What are the reasons? First reason is molecular weight of calcium carbonate is 100, easy for calculations. Second reason, it is insoluble in water. That is the reason why we have chosen calcium carbonate to express hardness of water. So, as calcium carbonate is insoluble in water, we need to add little amount of HCl to this. If we add little amount of HCl, this calcium carbonate can be easily dissolved in the water. Once the calcium carbonate, it will be dissolved in little amount of HCl, then we can add distilled water to the volumetric flask and make it up to the mark. One important thing you have to keep in mind while performing this experiment is you should never use tap water for making up the solutions. If you use tap water, there is possibility that we may not get the accurate result. And second thing is, there is possibility that precipitate also may take place. Precipitate formation may also take place. So, in always, not only in this experiment, in general, or in all the volumetric titrations, it is better to use distilled water. Especially in this titration, you should use only distilled water for making the solutions. So, in the step of preparation of standard hard water solution, we will be taking some 0.5 grams of calcium carbonate. It is dissolved in little amount of HCl and then distilled water is added and it is made up to the mark. Now, this standard hard water solution is prepared. Now, we need to find out the concentration, that is normality of this standard hard water. Let us represent it as N1. N1 means normality of standard hard water solution. And that it can be calculated by using the formula. Normality is always equal to weight of the sample or weight of the solute by molecular weight of the solute into 1000 by volume in ml. If the volume taken is in ml, we need to include 1000. If the volume taken is in liters, no need to include 1000. See, generally, normality is equal to weight by molecular weight into 1000 by volume. Volume means volume of volumetric flask. That is a solution we prepare in ml. If ml volumetric flask is used, then it is, we have to include 1000. If I take liters, 1 liter or 2 liters means volume in liters. These are the two important formulas. Okay. If volume is considered in ml, then we have to include 1000. If the volume is considered in liters, no need to include 1000. Okay. Here, as we are preparing 100 ml volume, as we are preparing the standard solution in 100 ml volumetric flask, no? That's why I have included 1000. So if I calculate normality, N1 is equal to weight of calcium carbonate. How much amount I have taken this calcium carbonate? Calcium carbonate is nothing but solute. I think solute plus solvent, it is called the solution. Solute is the one which is taken in smaller quantities and solvent is the one which is taken in larger quantities. Here, what is the solute that I have taken? That is calcium carbonate. How much amount I have taken? 0.5 grams. That is 0.55. What is the gram equivalent weight of calcium carbonate? 50. Gram molecular weight of calcium carbonate is 100. Gram equivalent weight of calcium carbonate is 50 into 1000 by 100. 100 is the volume of the solution, that is 100 ml volumetric flask we have taken and we have made it up to the mark, means 100 ml of calcium carbonate solution we have prepared. That's why I have included 100. So it will be 0.1 normal. Okay. So 0.1 normal of calcium carbonate standard solution we have prepared, means I know the concentration of this solution. Next step is standardization of EDTA. Standardization of EDTA means in this step, by using calcium carbonate which we prepared just now, by using that solution, we will be finding out the concentration of EDTA. Okay, EDTA is a secondary standard. We will be finding out the concentration of EDTA. How do we perform this? How to calculate the concentration of EDTA means, we need to take EDTA in the burette. EDTA, it is filled in the burette. Then the calcium carbonate standard solution which we prepared just now, 20 ml is taken out. 20 ml of the calcium carbonate standard solution is pipetted out in a conical flask, and to this EBT and buffer solution are added. This is a conical flask. In this, what we will be taking? We will be taking standard calcium carbonate solution, that is 20 ml. 20 ml of calcium carbonate solution which we just prepared now, no, that one we will be taking. We will be adding EBT indicator and also buffer. Ammonical buffer solution, that is 2 to 3 ml of ammonical buffer solution is added. Okay, now what will happen? Just recollect the principle. Wine red color is obtained. Means the calcium that is present in the water, it will combine with EBT indicator and form calcium EBT complex. As this calcium EBT complex is wine red in color, the solution will be wine red. Okay, now I will be taking EDTA in the burette and I will start titrating into the conical flask. Now what will happen? Blue color is obtained. It indicates that endpoint is reached. Okay. Now the formula to calculate the concentration of EDTA is N1V1 is equal to N2V2. Here N1 means normality of standard hard water. Now we know the concentration of we have prepared, no? This one. Now this value we already know it is 0.1. So the same value we will substitute here. This is equal to 0.1 normal. Volume of standard hard water. How much volume we have taken? 20 ml we have pipetted out. If you want, you can pipette out 10 ml also. Depending on your choice, you can take it. I have taken 20 ml. So here, instead of this V1, that is volume of standard hard water, I am writing 20 ml. If you have taken 10 ml, you can write it down 10. Okay. Normality of EDTA we have to find out. Now volume of EDTA, it is the burette reading. Okay, burette, we will be titrating it with the contents in the conical flask. No, once the end point is reached, we will note down the volume of EDTA that is consumed. Okay, that volume we need to replace it. This V2 will be the volume of EDTA consumed, that is burette reading. Now, regarding this burette reading, you need to keep one point in mind. Whether it can be any type of titration, acid base, precipitation, complexometric, whatever may be the titration, always the burette readings must be considered when we get concurrent values. What does this concurrent values means? First, we will take the contents in the conical flask and we will do the titration. We will continue adding the contents in the burette to the conical flask till endpoint is reached. Okay, when endpoint is reached, we will stop adding and we will take the reading of the burette, means volume of the solution in the burette that is consumed in this titration. Okay, for example, in the first titration, we will take up this one only. In the first titration, I got 16 ml of EDTA is consumed. Now again I will pour away the solution in the conical flask. I will take a fresh conical flask and I will add 20 ml water, indicator and buffer. And now I will again start titrating with the EDTA. And second time also it will consume some amount of EDTA it will consume to reach the end point. That volume, if I get 16, then I can consider, I will take it 16. For example, second time when I titrate, I got only 12. Then I need to repeat the experiment till I get same concurrent values. Same value must be obtained. First I got 16, next I got 12, again I got 13, again I have to repeat. Like that, fourth time again I got 13, then I will take 13 as a final value. Okay, so this is the meaning of concurrent values. Concurrent value means the same volume must be consumed, plus or minus 1, but same volume must be consumed during the titration. Okay, till I get the concurrent values, the titration must be repeated. This is done to get the accurate results. Just for accuracy, we will follow this procedure. So, this volume V2 is the volume of EDTA consumed. That one also we know we get this value from the burette reading. So, if we substitute all these values in this formula, we will get N2, that is normality of EDTA. Okay. Now, we know the concentration of EDTA solution. We have found out the concentration of EDTA solution from the standard calcium carbonate solution. That's why we have prepared calcium carbonate, just to find out the concentration of EDTA. Now, our real experiment starts. That is estimation of hardness of water. For this also, the same procedure. Hard water sample is taken, buffer, indicator. Again titrate with EDTA. Till concurrent values we need to repeat the experiment till concurrent values of the burette readings are obtained. Once we get the burette reading, the values are substituted in the formula. In here, N2V2 is equal to N3V3. Here, what is N2? This is the normality of EDTA. This one we have found out from the earlier step. That means from step 2, we have found out the normality of EDTA. This value we know. Volume of EDTA, this is nothing but the burette reading. We have already noted the values while doing the experiment. Burette reading also you know. Normality of hard water sample, we don't know. That one we have to calculate. Volume of hard water sample, we know. I have taken 20 ml. So, instead of V3, I will write down 20. So, by using this formula, we will calculate N3, that is normality of hard water. Okay, here normality of hard water means the concentration of hardness of water we are calculating. Here hardness means total hardness, that is temporary and permanent hardness. Concentration of the total hardness of water is calculated. Now, I want to calculate permanent hardness and temporary hardness both separately. I don't want both combined value. I want permanent value of permanent hardness and temporary hardness. So in order to calculate this separately, the next step is heating. You know, the temporary hardness, it can be easily removed by boiling, because carbonates are responsible for temporary hardness. When we boil the carbon dioxide, it will be eliminated. So the carbonate means a temporary hardness can be easily eliminated by boiling. So what I will do, I will take fresh 50 ml of hard water and I will keep for boiling. After few minutes, 10 or 15 minutes after boiling, the temporary hardness, it will be eliminated, and the water which is left over contains only the permanent hardness causing salts, because temporary hardness are eliminated by boiling. So the only hardness left over in the water is permanent hardness. So this permanent hardness of water I will calculate. The same procedure, whatever may be the step, the same procedure is taken. From after boiling, I will collect the water, I will bring it to room temperature, and then I will take 20 ml of that water into a conical flask. I will add buffer, I will add indicator. Why do we add buffer? To maintain pH 9 to 10. At that pH only complex formation will take place. If another pH is maintained, complex formation will not take place and endpoint can't be reached. So just to maintain that pH, we will add buffer. So in conical flask, what have we taken? 20 ml hard water sample. Hard water sample means that water contains only permanent hardness. Because of the boiling, we remove temporary hardness. Water sample, buffer and indicator. And we will titrate it with EDTA. Okay, blue color will be reached. We will stop adding EDTA to the contents in the conical flask. We will take the burette reading, that is volume of EDTA consumed. And that value, it will be substituted in this formula, that is N2V2 is equal to N4V4. N2 means normality of EDTA. The second step value, we have found it in second step now. That is normality of EDTA. That value we will substitute. Volume of EDTA, that is nothing but burette reading. N3 is the normality of hard water sample we need to find out. We need to find out the normality of hard water sample. V3 is the volume of hard water sample. How much amount I have taken? 20 ml. I know I have pipetted out 20 ml of the hard water sample. So I know how much amount is pipetted out, and I will substitute how much ever water I have taken. Okay, as already told, if you take 10 water, you have to write down 10. Okay, depending on the volume or quantity you have chosen. Now I got the N3 and it was written N4. Now I got the N4 value, that is normality of water containing permanent hardness. Now what I know the total hardness, that is N3. N3 is total hardness. N4 is permanent hardness. So it is easy to calculate the temporary hardness. Just a simple subtraction. Total hardness, it is the combination of permanent hardness and temporary hardness. So temporary hardness, if I want to calculate, it will be total hardness minus permanent hardness, that is N3 minus N4. Very easy to calculate. Okay, hope you all understood. Let me give a brief introduction. A brief recap. Hard water sample, EBT indicator and buffer solution. EBT indicator and buffer solution. Wine red color is obtained. We will titrate it with EDTA. Titration of the solution with EDTA. Blue color solution is obtained. Endpoint. Okay. The same, the important principle is, when the contents in the conical flask is hard water, means calcium or magnesium. Calcium or magnesium, hard water, EBT indicator, buffer. These two will combine and form unstable complex. Principle, unstable complex. When we start adding EDTA, these will dissociate and it will result in formation of calcium EDTA complexes that are stable. Okay. This is a simple procedure to calculate to estimate the hardness of water by EDTA method. It got the name EDTA method means it is the main reagent that is used in this titration. That's why it is named after EDTA method. Or complexometric method means this type of volumetric titration comes under the category of complexometric titrations. That's why it is also called as complexometric titration. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.